Okay, thanks a lot. Well, hello, everyone. Today, I am very pleased to introduce Carolina Cuesta. She is an old colleague and a good friend of mine from Durham University. Recently, she moved to MIT, where she's starting her postdoc. So Carolina, in cosmology, she has been working on redshift space distortion modeling. However, outside of the field of cosmology, she's also a bit of an expert in both machine learning and data science. Just to mention a couple of projects that she's been working on. She's been working with Amazon, for those that are interested. You know, Amazon, the big company. She was, if I remember correctly, working on Alexa, doing some machine learning stuff with Alexa. She also worked in IBEX, which is a medical imaging company in the US, doing some machine learning to try to improve the X-ray imaging that they did. And today she's gonna give us a talk about constraining vLCDM models. And well, without further ado, here's Carolina.
Thank you very much, Miguel. And thank you very much for the invite. It's a pleasure to be here. And I really look forward to the discussion after the talk. So as I said, I'm Carol, and I'm now a fellow at IFI. So it's hard to pronounce, and this is how you spell IFI. This is an institute shared among different institutions, so MIT and Harvard are both part of it. And the idea is to bridge the gap between AI and physics. So you have people working both in taking ideas from physics and applying them to AI, but also people working on bringing ideas from AI to physics. I'm more part of a second area. I'm working on bringing ideas from AI to cosmology. But today, actually, I'm not going to focus too much on the machine learning side. I'm going to be talking more about large-scale structure and summary statistics. But please feel free to ask questions or bring things up later when we'll talk. So in particular, I'm going to talk about a project I developed as part of the DESI collaboration with this group of people here, and in particular with Enrique Pailles, who is a postdoc at Waterloo. Let me start with the big picture of what we're trying to do. So first of all, DESI is going to observe, it's going to basically produce the most accurate three-dimensional maps of the universe. We're going to have millions of galaxy positions from which we expect to get cosmological information. So the idea is we have this three-dimensional map, and we want to constrain on the theory of gravity and its parameters. What we get in the end is two angles in scale and a redshift. So redshift can be translated into a distance from us. Ideally, we could measure the distance, but in the translation between redshift and distance, there is a further nuisance, which is that galaxies have their own peculiar velocities. So their light is not only redshifted because of the accelerated expansion of the universe, but also because they have their own peculiar motions. So that will introduce a further Doppler effect. And if we ignored it, we will actually find the wrong positions of galaxies. So this is what happens in an actual galaxy survey. So instead of getting the actual positions for galaxies, what we obtain what we call the redshift space positions, which is a combination of the actual position and the velocity along the line of sight of each galaxy. Now, this might sound like a big nuisance, and it probably is, so it is difficult to model. But at the same time, it is a very useful feature. So it allows us to get this information about the velocity field. The problem is that you have this joint information between density and velocity, and you have to decouple them along the line of sight. But it is, in the end, a very useful thing. Now, the obvious way to extract cosmological information from this three-dimensional map would be to compute its steepen correlation function. And what I'm going to talk about today is the fact that we know this is suboptimal in the range of scales that we want to explore with DESI. So we're going to be talking about what we can do instead of computing the steepen correlation function. But first, let me tell you why we really want to constrain these cosmological parameters as accurately as possible. So nowadays, we can basically compress the whole information about how the universe evolved into 5 to 10 parameters. Here we have a summary of some of them. So 2 of them are basically describing the initial conditions of the universe and its astrophysical properties. And others are describing its dynamics, right, how it evolves. And this is all very elegant and nice, if only we knew what these parameters actually mean. So here, I'm sure you're very well aware that we don't really know what dark matter is made of or what dark energy really is. So what we want to do is constrain these parameters really accurately to see where the theory breaks down. And how will we know that it breaks down is by comparing different data sets. So for instance, one of the measurements that are very important currently is the growth rate of a structure in the universe. So this F of Z, so Z, the x-axis is redshift, and F is the rate at which structures grow in the universe. What you see is the Planck prediction in the background. The Planck is a measurement of the early universe, the CMB. You can take the parameters that we predict from the CMB and extrapolate them to later times using a model, vLCDM. And then we can actually produce measurements of this value F, the growth rate, using galaxy clustering. So something like DESI, but in the past it's been BOSS. Most of these measurements actually come from BOSS somehow. And you see that actually they tend to be lower than the Planck measurement. However, the error bars are still quite large. So that's why we want to reduce the error bars. We want to see whether this is actually a significant tension or it's not something we should worry about because they're actually statistically consistent. And the only way we can know that is by reducing these error bars. So it's not only a matter of getting more precise measurements because we want it, but because it could mean that we might find a signature of where vLCDM breaks out. Right. Apart from that, there's a lot more we can learn from large-scale structure. So we could find a signature of modifications of gravity on large scales. And actually the growth rate of structure is a really good probe of whether gravity has been modified. You can think of growth as a competition between gravity pulling things together and the expansion pulling things apart. Now, if the background expansion is fixed and you modify gravity by you introduce basically additional gravitational forces, you're going to change that balance and the growth rate is going to be modified. So you could find that signature there. Measuring the mass of neutrinos is actually the first evidence we have beyond the standard model of physics, the fact that neutrinos have masses. And large-scale structure of the universe might provide the most accurate measurement that we will have in the future, because this actually is something really hard to do in experiments in the laboratory. So that makes it very exciting. Primordial non-Gaussianity is one of the other things that we might be interested in to probe the physics of inflation. And finally, galaxy formation. So we tend to treat galaxy formation as a nuisance to all of our analysis, but at some point, there'll be a lot we can learn about it by looking at the large-scale structure of the universe, and we should also try and learn from it and not just marginalize over it. Right, so I hope I convinced you of the fact that there's a lot of information that we can extract from the large-scale structure. Now the question is, how do we optimally extract it? Let's look at the properties of the density field first before we're going to answer this question. If we look at the very early universe, so CMB basically, and we look at the density fluctuations, so delta is the over density at each point, what we find is that delta can be very well described by linear theory. So we start with some initial density field, we can linearly propagate it to a later time. Also, this delta is distributed as a Gaussian distribution. Now, what happens as gravity kicks in? So what happens is that this Gaussian distribution has to get skewed because voids can't be emptier than empty, right? So this distribution is bounded by -1. And what's going to happen is that voids are going to be growing in size and peaks as well. So you get this skewed distribution. And this has very important consequences because it changes the statistical description of the field. If we look at early times, because the density field is Gaussian, you can replace the whole density map by just a 2-point correlation function or power spectrum, so 2-point functions. So this step is lossless. We haven't lost any information about cosmology in performing the summary. However, when we look at the late universe, because the density field is non-Gaussian, when we do the same step, so either compressing it into a 2-point correlation function or power spectrum, so they're just the Fourier transform of each other, we're actually losing information just because the field is non-Gaussian. So this information is not optimal, and it's something we shouldn't be doing with a large-scale structure. Now, what can we do instead? So what we're going to be looking at is a statistic that is environment dependent. So when I showed you this PDF and how it develops skewness, how the different densities in the universe develop, there is a lot of richness of information there in what is happening in each of these environments. And we're going to try to explore how clustering changes in each environment. So how does it look like in voids and in clusters in a more continuous manner? How do we do that? So we start with a sample of galaxies, like the ones you see here. We're going to sample random points around them. So whatever, if it's a simulation, you will sample random points around the simulation box. If it's an actual survey, you just place your random points around the mask of the survey. And now we're going to measure the density around each of these points. So in the spheres of a given radius. So for instance, most of the time we'll be using radiuses of 20 neoparsecs. And then we group these points ranked by density. So for instance, those belonging to the lowest density group will be number 1, and those belonging to the highest density group will be number 5. 2, 3, and 4 are all in between. So we've made 5 groups, quintiles of the density field. This is how the density PDF looks like. So we plot the density in each of these spheres in a histogram. It look like this. So again, you can see voids here in DS1, what we call the first density split, and DS5 would be something more like clusters. In this case, the radius was 15 megaparsecs. And you can see that if you make this radius larger to something like 80 megaparsec, this distribution becomes very much like a Gaussian. So on large scales, the density field is very much Gaussian. On smaller scales, this isn't the case. And actually, there's a lot of cosmological information already at the PDF level. So this is what people call the one-point function. And you can see a series of paper here by Korat Williman on how to extract information from it and how constraining it can be beyond two-point functions. Right, so where are those points? So as I said, so this is one of our simulations we're looking at. This is the dark matter density field. And I'm showing where the points in each quintile appear in the simulation. So DS1, as I said, very much tracing void-like regions. So you can see that the points fall mainly where voids are, under the dense regions. Whereas DS5 is basically tracing the nodes of the cosmic web or clusters. Right, so what can we do with our random points now? So we can, for instance, compute correlations. So autocorrelations of points in the same group. You can see how they look like here as a function of pair separation. And basically what you see is that the signal is largest for void-like and cluster-like regions. And you can see clearly the BAO peak here at about 90-100 neoparsecs. And then what happens in between is much lower signal. Now we can also cross-correlate the positions of each of the groups, of random points in each of the groups, with the galaxies. So this would be similar, for instance, to a void galaxy cross-correlation for those points belonging to the density split one. Now, because the galaxies are in redshift space, so we have the redshift space positions of galaxies, the two-point correlation function is no longer going to be isotropic, right? You're adding this special direction, which is the line of sight. So it's going to depend actually on not only pair separation, but both pair separation and angle with respect to the line of sight. What we do is just take monopole and quadrupole to have a look at how it varies with scale. It's a way to compress the two-dimensional information. So if we look at the monopole and quadrupole, let's focus first on the monopole, which is easier to understand. You can see here that for points, it's actually very unlikely to find a galaxy around the void, as you will expect. That's why it is negative. Whereas it is very likely for cluster-like regions. Again, you see the BAO peak in each of these environment regions. And you can see also what happens to the quadrupole. Again, the signals are largest for DS1 and DS5, so the most extreme environments. The case of the two-point correlation function would be some sort of weighted average of these curves. So normally you're averaging out all this information in the two-point correlation function. Another question we have is, how much cosmological information do these different observables compare to the two-point correlation function? So it is actually more constraining, or is it actually not that useful? So we're going to be looking at that using n-body simulations and the concept of Fisher information. the idea is that we don't really know how to model these curves as a function of cosmology from first principles, but we can obtain them from simulations. So we can use simulations to measure the information content of this statistic. And in particular, what we do is measure the Fisher information. I'm going to just tell you what is the general idea of Fisher information. The idea is that you have a likelihood of your data X, given your parameters theta, and you can extract the maximum likelihood point by setting the derivative to 0. Now, because your data is a random variable, your likelihood is going to look different, depending on the sample of the data that you get. In the universe, we only get one, right? But you can see what happens in simulations. Now, how do we know, just seeing one point, how informative this statistic is? Like, how tight are your constraints going to be? Well, it's actually very simple, because what we care about is how peaked this likelihood is. So if it's very peaked, it means we're actually going to be able to constrain those parameters really well. If it's pretty flat, we won't be able to constrain. So that's the idea for the Fisher matrix. So it's basically the expected value of the second derivative of that likelihood, so its curvature. And for Gaussian likelihood, this can be expressed as the derivative of the summary with respect to the parameters, so this first term here, times the covariance inverse. So it's very easy to compute. What we've done is check that the likelihood of this statistic is actually very close to Gaussian, and it is. So this approximation is actually valid. And now we can focus on measuring these different ingredients from simulations to just find the cosmological constraints that will be given by the inverse Fisher matrix. All right, so what simulations have we used? This is the Quixote suite of simulations. So they were exactly developed to produce Fisher forecasts. That's why you have a set of fiducial cosmologies. So you have loads of realizations of the same cosmology where you could compute covariance matrices, assuming that the covariance doesn't change with cosmology. And then you have what we call derivative grid simulations, in which you vary one parameter at a time, plus and minus, so that you can estimate the derivative with respect to each of the parameters. And you also have a neutrino masses, so you can also estimate how well you can constrain neutrino masses. Right, so let's look at the derivatives first. We need to compute the derivatives of monopole and quadrupole, of autocorrelations and cross correlations for each of the parameters we want to constrain. This is for one example of how it looks like for omega matter. And the way we compute is just find the differences, right? So you have a simulation, you can measure the summary from a simulation where omega matter is higher and one from omega matter is lower, and compute the derivative. Same for the covariance. You measure the summary in your simulations and you estimate the covariance. So here you can see different covariances between DS1, DS2 at different scales, etc. It's a very complicated covariance matrix, so I don't expect you to understand it by just looking at it. Right, so now we're going to look at the final constraints. So this is how the constraints look like for the T-point correlation function. We're here using a minimum scale of 10 megaparsecs. We didn't want to use smaller scales because we're actually looking at dark matter halos. But we know that galaxies populate dark matter halos so this is what we call the one halo term, right? And that's not going to be in our dark matter halo. So we didn't want to really look at those very small scales. And we know that's going to change with galaxies. Right. So in these plots, what we care about is not the mean value of these constraints, because that doesn't really mean anything, right? This is the fiducial cosmology of your simulations. What we care about is the error bars. So how precisely can you constrain your parameter? And for the T-point correlation function, you can see that there are lots of degeneracies between different parameters. So for instance, if you look at the omega matter sigma 8 plane, you can see that degeneracy is very strong. But what happens when we replace the T-point correlation function by these environment-dependent correlations? Well, this is the result. So the constraints become much, much better. You can see that for some parameters, like sum of neutrino masses improvement is really, really large, or for omega matter. So how did this happen? Is this just pure magic? What is happening? Well, we can look at the constraints from different environments. So here in yellow, we have the constraints coming from void-like regions. Whereas in green, we have those coming from cluster-like regions, right? So the lowest density environments and the highest density environments. And you can see that they are actually very complementary in some cases. So they really help us break some of the parameter degeneracies that we saw at the level of the two-point correlation function. So for instance, if you look at the plane of omega matter with massive neutrinos, with a massive neutrinos, then you can see that they're pretty much perpendicular. And that happens for many different parameters. So actually, different environments are responding differently to the cosmological parameters, and that really helps constrain them. Whereas in the case of the two-point correlation function, you just average out all of that. Right, so let's look a bit more about where the information actually comes from. Here you can see how the constraints on omega matter and sigma 8 will change with the minimum scale. So what happens if we only include large scale, so for instance, minimum scale of 100, that will mean we're just looking at the PO compared to when we include the whole range of scales. And you can see that as expected, the constraints always get better. What might sound a bit strange is why the constraints so much better on large scales. So I told you earlier that the density field on large scales is pretty much Gaussian. So shouldn't the two-point correlation function be optimal for a Gaussian density field? Well, it's a bit trickier than that, the comparison. But we actually looked at how does this statistic look like for Gaussian random fields and what should we expect there. So this is measurements produced in some mock Gaussian random fields that have the same two-point correlation function than that of Quixote, so a full embodied simulation. And as expected, everything is symmetric. So this Gaussian, right? So DS1 and DS5 are behaving exactly the same way for both autocorrelations. So this is the first panel, is the autocorrelations of random points. And the lower panel is the cross correlation between the points and dark matter halos. Again, they're fully symmetric. Now, when we compare the information content, if we use the whole range of scales, the two-point correlation function and density split are performing very similarly, as you can see here, up to like numerical precision. So it's really it's working as expected, right? The two-point correlation function is optimal in the case of the Gaussian random field. However, when we look at larger scales, so imagine if we include scales down to 10 megaparsecs but remove anything below 10, then if you compare the blue and the red contours, you can see the density split is actually doing much better again. So why is that? Well, this is happening because when you split your densities in quintiles, you're computing the density in spheres of 20 megaparsecs. So you're already using the small scale information. So it is actually unfair to compare a minimum scale cut because that information is already there in density split. And that's actually what you can see in the green contour. The green contour, we added the mean density in each environment to the two-point correlation function. And you can see that in that case, density split is performing very similarly to the two-point correlation function plus the average density in each environment because it has that small scale information. So there's nothing odd about it performing better than the two-point correlation function on large scale. So I'm going to move on to a different question. And it's that I have been cheating so far. I haven't told you that we can't actually compute the densities that easily. Because we were using simulations, so far, we were using the real space positions of galaxies to estimate the density. As I told you, we don't really know where galaxies are exactly, because along the line of sight, we get the effect of redshift space distortions that plays around with where the galaxies actually are. So in reality, we get something distorted, distorted positions of galaxies, and we still need to estimate the density. So how different is the density estimation in redshift space from real space? So we can look at the grouping of random points in the different groups and how it changes between real and redshift space. And this is what you see in this matrix here. So what you see is how many points that were classified as belonging to the lowest density group in real space actually belong to that same group in redshift space. That would be this item here, 84. So I'm telling you that 84 of the random points, 84% were classified as belonging to the same group, but 14% of them move between DS1 and DS2, and it is even higher for the quintile. So actually they've been mixed up. And that could, in theory, reduce the cosmological information in the parameters you're interested in, because it could make the signal noisier. And that's something we wanted to test. So that's something we can do using, again, same Fisher forecast, but measuring the densities in redshift space instead of real space to make it more realistic and closer to what we actually could do with observations. So this is actually a problem that people have in void studies as well. So when you have to detect voids using galaxy positions, you have to be careful because the voids you identified using the real space galaxy positions and the redshift space ones are not the same ones. So it's exactly the same problem here. Right, so how do the different statistics look like? So here you're looking at the cross correlations between the random points and the dark matter halos, monopole and quadrupole. And you see here R split is what we were doing so far, using the real space positions of galaxies to determine their density. And Z split is what happens if we actually use the redshift space positions of galaxies to estimate the density and group them into quintiles. So for the monopole, they actually are pretty similar. So on small scales, there are some differences, but they're pretty similar. But the quadrupole is really very different. And again, this is the same thing happens for void galaxy cross correlations. What you can see is that the signal in this redshift space split, Z split, on the quadrupole is much larger. So why is this happening? This is happening because the distribution of random points in each quintile is not isotropic anymore because of the effect of redshift space distortions. So you have an anisotropy there in the first place that is only going to be incremented by the galaxies when you cross correlate them. You can see that in the autocorrelations as well. So this is the autocorrelations of points belonging to the same group, the same quintile. And again, the monopole looks very similar, but if you look at the quadrupole, although in R split 0, because points are isotropically distributed, they're not 0 when you identify them in redshift space because they're not isotropically distributed anymore. You have this line of sight effect. So although our quintiles have been mixed up by the effect of redshift space distortions, and that might mean we might end up losing some cosmological information. At the same time, this signal in the quadrupole, so how much more anisotropic they become when you identify them in redshift space, also contains cosmological information. So the question is, how much do these two go against each other and who wins in the end? So can we just do the analysis completely in redshift space and not worry about it, or are we losing too much information? So that's the question we can answer with the same Fisher machinery. So this is how the final constraints look like. You can see again the steepen correlation function, and now we're comparing Z splits. So if we do everything in redshift space, identifying densities as well, to R split. So R split is what we were doing so far. And you can see that for some cosmological parameters, you actually do lose some information by doing everything in redshift space, like omega matter. But this is actually a very small difference. And for most parameters, you actually don't lose information, like, for instance, the sum of neutrino masses, the difference is very, very small. And this is very good news, because that means we don't need to worry about how we're going to estimate the real space density of the random points, but we can just use the redshift space positions and not lose much information. So this is very interesting. Also, because we intend to base all our models in simulations, we don't need to worry too much about how do we model these effect of redshift space distortions on identifying densities, because we can just extract it from simulations. So it's good news. I'm going to show you now some constraints and some comparison with other work of people have been doing, working with different summary statistics to go beyond the 2-point function. So at the bottom, for instance, you can see the void steepen correlation function, so the void autocorrelations, and void halo cross correlation function. So that would be something similar to our first quintile density, but we have a more continuous version of that. And you can see how the constraints really are much better. And especially if you look at the sum of neutrino masses, we're getting really, really good constraints compared to the supreme correlation function. So this is potentially a very, very accurate test of massive neutrinos. But again, this is a Fisher forecast, so we need to actually make sure that this works when we move to actual observations. Right, and how are we going to do that? So, as I said, we want to base our model on simulations because analytical models will only work on very large scales, and we want to make sure that we capture the information that we saw was inside the small scale clustering as well. And because modeling this real-to-redshift space mapping is actually quite complicated, we would like to base our model on simulations. So we basically want to build a forward model of the data using simulations, and then invert the problem to obtain a posterior under cosmological parameters. But actually building a forward model is very challenging. So if we start from dark matter only simulations, how do we produce something that looks like the observations? So the galaxies that we observe. So first we need to worry about the galaxy halo connection. So how are we going to populate the dark matter only simulation with realistic galaxies? And what effects could that have? So the choices we make in that aspect could translate into biases in the cosmological constraints. We need to worry about Alko-Paczynski as well. So the fact that when we translate angles and redshift to distances, that depends on the cosmological model that you use. And if the cosmological model that you use is not the correct one, you're going to end up introducing some additional anisotropy apart from redshift space distortions. That's something we need to include too. Light cone effects also cut sky, right? So the fact that we only observe certain parts of the sky, and systematics like fiber collisions coming from DESI. So these are all things we're looking at, and how do we include them in our formal model? This is current work. You can see here, for instance, the measurement of density split in BOS. So although we're developing everything for DESI, we're first going to test our pipeline using BOS data because it's been widely used by other people before, and we can easily compare constraints. They have a handle on systematics as well. And what you see here on the left-hand side is the number density of galaxies as a function of redshift, and the number density of random points as the function of redshift 2 belong to each of the quintiles. So you can see that they all follow closely that of what the galaxies are doing, which is what we expected. On the right side, what you see is basically the footprint of BOS. So this is the area of the sky that we observed. And we're just showing that you get these random points everywhere, same as galaxies, which is good. Here you can see what the PDF looks like if we look at the CMAS galaxy samples, so in redshift between 0.46 and 6. And we're looking at the density in spheres within 20 megaparsecs in redshift space. So now we're estimating density directly in redshift space because that's what you get from a galaxy survey. And you can see here the different groupings we have made based on these densities. Right, this is how the actual measurements look like of different. This is the cross correlations between the random points and the galaxies. And again, you can see the BAO at different environments and the quadrupole. What we're trying to do now is fit the model to these different multiples, especially trying to use the whole range of scales. So far we've been working with scales down to 30 megaparsecs, and we're trying to push it to even smaller scales to get these constraints on BOS data. And how do we push it to those very small scales? Well, first we need to worry about the galaxy halo connection. As I said, we start from a dark matter only simulation, and we somehow need to identify bound structures, what we call dark matter halos, and populate them with galaxies. So we've been using an halo occupation distribution model, so-called HOD, to determine what is the mean number of galaxies as a function of halo mass that we need to sample for each of these halos. So the distribution of central galaxies parameterized by 2 free parameters. So that tells you what's the mean number of centrals you will expect per halo. And then we have another set of galaxies that are orbiting around the main halo, which are called satellite galaxies. And their distribution is parameterized by three free parameters. Now we like the most basic HCD model that you can construct. But we have made some important assumptions. One is that formation of galaxies doesn't impact dark matter clustering, right? So we're simulating dark matter and then adding things on top. But galaxies could have had an impact on that dark matter clustering in the first place. And we know from hydro simulations that it does, but it's a very small effect down to a small scale. Now, the second assumption we've made is that the mean number of galaxies depends on the mass of the halo only. But again, from hydro simulations, we know that that's not necessarily the case. It could depend on other properties of the halo, such as concentration, when did it form, or other properties. So these are all things that we need to test by checking that even in cases where these assumptions break down, you still can recover the right cosmological parameters. In general, you can extend these models by getting creative. So you can think of velocity biases. So maybe these galaxies don't have the same velocities as their parent halos. Or assembly bias, as I said, the mean number of galaxies each halo hosts could depend on properties like environment density, concentration, or formation time. So you can get as creative as you want. Problem is that as you get creative, you amend your parameter space, and that means you might be limiting your constraining power in the cosmological parameters. So now what can we do? So on one hand, we can use hydro simulations to kind of limit our options. So we can check what are the most plausible scenarios of galaxy formation using hydro simulations and just be guided by them. Or we could think of ways in which we can match the data to optimize for robustness. So for instance, what we've been doing for many, many years in cosmology is just mask out to small scales, right? So only analyze large scale data. But in the future, as you go to this more complicated summary statistics or even field level inference, you might be doing like different masks, right? That make your data your inference more robust. But yeah, that's all an ongoing debate in the community, and I'm sure we're gonna get more and more ideas on this front. It's probably one of the most important topics at the moment. How do we deal with galaxy bias properly? Right, but apart from that, so if we assume the galaxy population model, basic HCD with some extensions on assembly bias, etc., then we can, based on about 100 embedded simulations, use neural networks to map the cosmological parameters and the HCD parameters into our summary statistic. So you basically measure the summary statistic in each of your simulations with varying HCD parameters, and then fit the neural network to it. Then you can assume a Gaussian likelihood and obtain constraints on the cosmological parameters. So this is ongoing work. It's something we're doing currently. So you try and get constraints from BOST. Yeah, stay tuned. We'll hopefully have some results soon. Now I'm going to move a bit more into more speculative things that we should be looking at and we will be looking at in the future. One is how important is the assumption of Gaussianity we have done in the likelihood. So for Cuban correlation functions, we know the assumption is not too bad, but actually, once you add survey systematics, it becomes a bit difficult, right? So likelihoods are rarely just Gaussian. But what we can do is use the simulations to learn what the likelihood of any summary statistic actually looks like. And you can do that by using models like normalizing flows. So normalizing flows are basically models that map one probability distribution that is normally taken as Gaussian. So this is a latent distribution that you sample from, and it's a Gaussian. It's taken as a Gaussian because it's just easy to sample and evaluate. And then you can use neural networks to transform that random variable into your data, X. So you basically deform the Gaussian using just change the variable room to make it look like your data. So if you write it down, X, your data, is the transformation of this latent variable Z, and it can also be inverted. So you can evaluate likelihoods, etc. So for instance, if you want to evaluate the likelihood of X, P of X, you will take P of Z, which is a Gaussian you can evaluate very easily, and the inverse function of your neural network using the determinant, then you'll get P of X exactly. So actually, there was a recent paper called SIMBIG that came out last week using these sort of methods to estimate the posterior of the power spectrum in the both survey as well, using a full forward model with all the survey systematics. It actually can work pretty well for cosmology, and that's something we need to test, especially with these alternative summary statistics that might have likelihoods that are not Gaussian at all, and that could really, really bias our constraints. So these soft models don't make any assumptions on the likelihood. Bear in mind that probably likelihoods are rarely just Gaussian when you take into account all the survey systematics. And it also means you don't need any like expensive MCMC chains to estimate the posterior. So if you are modeling the posterior directly with the normalizing flow, then you just need to sample from a Gaussian and transform it. That would be your MCMC to get estimates of the posterior. So this is definitely a very interesting class of models. But even thinking beyond summary statistics, so if we look at the data itself, we have kind of a point cloud of galaxies from which we could build a neural network to learn a representation or optimal summary statistic from which we can obtain a posterior on the cosmological parameters. The idea is that as we move into more complex summary statistics, it's going to be very hard to combine the constraints, right? So we can have constraints from void galaxy cross-correlation, from density split, from anything you can think of the bias spectrum, but none of them are necessarily optimal. So we can use machine learning to actually find what is the optimal set of constraints by using embodied simulations again. And the idea is that we can think more carefully about the structure of the inputs. So what we have an input is not really an image, so it's not suited for a convolutional neural network. It's more like a point cloud or a graph where the nodes are at galaxy. And thinking about the structure could actually help us interpret what the network is actually learning. And it can be very helpful as well to model the cross correlations between different surveys. So here you can see lensing, for instance. It's actually very challenging to combine data from different surveys and do inference because they have different systematics and different issues. But at the level of the field, using machine learning, this could actually be pretty simple and a very interesting thing to do. So I'm gonna finish here with just the things that I think machine learning can do for cosmology. So I think it's definitely already used to accelerate nonlinear prediction. So all these sort of emulators like the one we're using for density split, but many people are working on this sort of emulators. They all use machine learning to some extent. So either neural networks or Gaussian processes. While we're going further, we can also use them for density estimation to lift the Gaussian likelihood assumption and see what the consequences are from different alternative summary statistics. But going beyond, we can use machine learning to aim at extracting all the information that there is at the field level in the fully nonlinear regime, and hopefully use it to compare the data and our simulations. So in the end, we kind of know that our simulations are not perfect and they don't reproduce the data perfectly. So can we use machine learning to kind of guide us and point us to what is missing in our simulations to actually reproduce the data? And having said that, I'm going to stop here and look for all your questions. Thank you.
Okay, hello everyone. Thanks a lot, Carol, for this very interesting and amazing talk. While everyone is gathering their thoughts for questions, please raise your hands if you have any question. I would like to start with a couple of very probably naive questions. So you mentioned in this quantile method that you are using that you divide your data into 5 sets. I'm guessing this means that each of your statistics has like larger error bars that what a correlation function could have. So does this affect your measurements in any way? Like, are we doing this only because DESI has so many points that we can do it now, or do you have something to say about that?
Right, it's an interesting question because actually the opposite, because we're sampling random points. So we can sample any number of random points. We can basically sample as many as we get to saturate cosmic variance, right? So you have cosmic variance and some sample variance, but we can reduce sample variance as much as we can, which normally happens when you have 5 times as more random points that you do galaxies. So actually your errors are even smaller. And that's why, for instance, building an emulator is challenging, because the error bars are so small that your emulator needs to be super precise.
All right, thank you very much. So I see that we have a couple of questions. Maybe William, you can start with your question.
Right. Thanks for a really nice talk. I have a kind of related question. So this density splits, I was curious how you choose threshold values for these splits, and maybe if you change the number of splits, say from 5 to 6 or 4, how would that affect the constraint?
Right, yeah, so the way we split them, so how you choose what density range goes in each quintile is by having the same number of points. So they're actually quintiles of distribution. So you have the same number of random points in each of the groups. You could also set a density threshold, but then you will have to find which ones are the optimal ones, right? And yeah, it's not clear which one would be, and you'll have different number of random points in each group. I'm sorry, what was the second question? Why 5 and whether we've tried a different number? Right. Yeah, so you could have a larger number or a smaller number, but I doubt, I mean, there's a point in which there's not going to be much gain, right? And you're going to need many more random points. So far it's been a question of computational tractability, right? So to not make things slower, we've left it into 5, but you could definitely add more, and perhaps your constraints would be slightly better. But we haven't played around with that much.
Thank you.
Next is Rodrigo.
Hi, thanks again for a very nice talk. So it's really interesting the constraints you get on the neutrino masses. And so I was wondering, so I mean, it's known that the hierarchy of neutrino masses affect cosmological constraints. So I was wondering if you can, I mean, if you have a feeling of what would happen. I guess these Quixote simulations assume normal hierarchy. What would happen, and could you be able to tell something about the hierarchy of neutrino masses using this type of density split measurements? So yeah.
Right, it's a very good question, because in the end, that would be the interesting thing to learn from, right? Like properties of neutrinos, not only the sum of their masses, right? Problem is that we don't really know, because we can only go as far as the simulations go, right? So if the simulations made those assumptions, we would need new simulations with a new set of assumptions. I'm afraid I can't say much more than that.
So there are no simulations using different hierarchy of masses? I mean, I don't know nothing about simulations. So.
Not to my knowledge. I think, well, actually, to the degree we're testing the sum of neutrino masses, it might not matter. In the effect in clustering might be the same. So we might not be able to test it. I'm not quite sure. Yeah, I'm not afraid I can really answer the question. Sorry.
Okay, thanks.
Next, Benedict, do you want to answer your question?
Yep. Hi, Carlos. Thanks for the great talk. I had so you're measuring the monopole and the quadrupole. Did you consider extending measuring the monopole? I think, considering that Florian is in your list of authors, to test the gravitational redshift in the voids. Or do you think that would be something that would be feasible, or do you think it would be too noisy? Or I don't know whether you can actually do that with density splitting. I only knew that if you had different populations that you could do that, but so would that be something that you could do with density splitting in principle, and do you think it would be feasible?
That's completely right. Yeah, so that's something Florian is thinking about, because you need this sort of like multi-tracer thing, right? Where you have different samples with different biases. And that's exactly what you get with density split, different biases. And also because I think the efficiency of the constraints were highest for a sample with bias close to 0, with a very small bias. And that's actually what we get for something like DS3, so for like the quintile in the middle. So yeah, it's actually something very interesting, and I'm sure we'll look at more in the future.
Well, I guess you have to then do GR simulations. That might be.
Or because you only care about large scales, you could actually use an analytical model for the density split. So on large scales, you could do everything analytically.
Ah, cool. All
So
right.
hopefully that should be okay. Yeah.
Yeah. Cool. Thanks.
Okay, I don't see any more questions. So I think we can, given that it's almost an hour now, we can probably move to to have an informal chat with our speaker. So maybe